Alright guys, welcome back. Today we're going to be focusing on electrolytic cells. On Thursday, our lesson 14, we focused on voltaic cells. Today we're going to be focusing on electrolytic cells. So, this is what our objective is. Our do now is asking us to differentiate, go ahead and label this voltaic cell. Now, this is obviously not what it looks like in your notes, but it's very similar to it. So the first thing I want us to do is being able to label our anode and our cathode. So if we remember from lesson 14, our anode is our most active element according to table J, the activity series, and our cathode is the least active according to table J, the activity series. Now, for us to determine this, all we really need to do is look at table J. So if we go ahead and look at your table J to determine which one is your anode and which one is your cathode, once again, because I do not have the reference table on the slide, I'm looking at it on the side on my phone. And the way table J works, again, for the people that are a little bit confused, the higher you are on table J, the more active you are. The lower you are on table J, the less active you are. So we have cesium and nickel, and cesium is more active than nickel. So that makes cesium our anode and nickel our cathode. I'm going to go ahead and label that. So with that being said, yep, we got our anode here, and we got our cathode here. Now our anode is our negative electrode. There we go. And cathode is our positive electrode. So there we go. Just a little reminder to help us. Now, number 2 says identify the salt bridge. Well, we know the salt bridge is what allows the flow of ions. Now, the flow of ions, I'm not talking about Ni+3 or Cs+1. I'm talking about the ions that were attached to them in the solution, so the electrolytes. What is that? That could be nitrate or sulfate. That's what's flowing in between the cells through the salt bridge. It's preventing the buildup of ions as well. So letter B would represent our salt bridge. So I'm going to go ahead. I circled it, and then I'm going to write CB right there. Now, it's supposed to say number 3, but it doesn't. It says indicate the flow of electrons. Well, we know that if we were electrons, we're going from the negative to the positive. So we're going from our anode to our cathode. Now, anytime we're going from our anode to our cathode, I don't want you to mention anode to cathode. I want you to mention from the species to what species. So in this case, it would be from cesium to nickel. Now, there might be a couple of questions that ask, okay, which one is going to gain the more ions, or which one is going to have a mass increase? Well, cesium is losing 2 electrons. So cesium would decrease in mass. Cesium would decrease in mass, but it would increase in ions because it's losing 2 electrons. As the electrons is lost, the atom becomes an ion. So cesium has an increase in ions, while nickel will have a decrease in ions, but an increase in mass, because as we're sending those 2 electrons over to nickel, we are gaining 2 electrons every single time. So the next part asks us to write the half reaction for oxidation and the half reaction for reduction. Perfectly fine, but we need to know where that is happening at. So, remember, an ox, red cat, meaning anode is where oxidation takes place and reduction takes place in a cathode. So we have that information. Let's go ahead and write our half reaction, and the ion and the atom should be able to help you. So for oxidation, we are going to go from CS yields CS plus 1 plus 1e minus. That's oxidation. Then for reduction, we're going to go Ni 3 plus 3e minus yields Ni. That could be Ni0, or it could just leave that as Ni. I feel like writing the zeros. You know you've written your half reactions correctly if you can clearly see that you are reducing or you are oxidizing. Remember, once you become more positive, you're oxidizing. Once you become more negative, you are reducing. So this is very similar to our do now. This is actually what you're do. No, this is similar to your do now as well. But we're gonna go ahead and skip that, and let's get to electrolytic cells. So electrolytic cells. This is a summary. In your notes, you have a reading there as well. So electrolytic cells turn electrical energy into chemical energy. And it's through a non-spontaneous reaction. So unlike voltaic cell, which was a spontaneous reaction, meaning because we have one metal that's more active than the other metal, the reaction kind of happens on its own. However, for electrolytic cells, the reaction does not happen by itself. It needs an outside source. So for the outside source, that outside source to power the reaction, you're always going to need a battery. You're always going to need a battery, which is right here. Now, electrolytic cells are used for multiple things. So those things are electrolysis and electroplating. Now, electroplating is the process of transferring color onto a weaker metal. You've mostly seen this with gold-plated chains or silver-plated chains or bracelets or earrings, right? Even though the material that is being created or being used is not a proper material, it might be copper, it might be a cheaper metal, they always have this goldish color to it, and that's always due to the electroplating. We're transferring the gold color onto the weaker metal. Now, that doesn't mean that the material is actually gold. No, it just has the appearance of gold due to electroplating. Electrolysis, there's two types of electrolysis. Electrolysis is a chemical decomposition which involves the use of electric current. So we have the decomposition of water, where you have H2O is actually technically being separated into hydrogen and oxygen. And then you also have the decomposition of ionic compounds, which is where we can get Na and Cl to break up into actual Na and Cl. So those are the two reactions that are involved with electrolytic cells. Now, this is our electrolytic cell right here, right? And I'm gonna summarize this, and then I'm gonna go read the notes from the other slide. So we always are going to have the anode and the cathode. Now the anode in this case is going to be positive, and the cathode in this case is going to be negative, which is obviously different from the voltaic cell. The electrons are going to leave the anode, travel through the wire, through the battery, and go into the cathode. And both electrodes are going to be sitting in an electrolytic solution, meaning it can produce electric current that contains a lot of ions that are just floating around. So, like I said, there's two parts of the electrolytic cell, while in the voltaic cell we had three parts. So the electrolytic cell, the cathode, like I said before, is sending the electrons over. The cathode is where the electrons are being sent. So the cathode is gaining electrons. It is the negative electrode, and it's still where reduction takes place. So we're still following red cat. Anode is where the electrons are being taken from. So anode is where the electrons are being taken from. It is the positive electrode, and it's where oxidation occurs. Still going with anox. The only difference between an electrolytic cell and a voltaic cell is that electrolytic cell you can clearly see the battery, while a voltaic cell you can clearly see the salt bridge. Remember, an electrolytic cell needs an outside source, and that is going to be a battery. And it's very funny because a voltaic cell is also known as a battery. So in a way, you need a voltaic cell for an electrolytic cell to work. Think about that. All right? So, let's go ahead. Let's practice this out, and then we're going to go ahead and differentiate an electrolytic cell from a voltaic cell. So, which reaction occurs at the anode? Well, if I remember, we have acronyms in chemistry that would help, especially in this unit. So we have anox and red cat. That means oxidation is going to happen at the anode. And that means reduction is going to happen at the cathode. Alright, so that was easy. That was a summary question. C. Label the anode and the cathode on the lines with the arrow. Now, you're like, okay, how am I going to label the anode and the cathode? Well, we already know that we have silver there, and then we have a spoon right here. So I don't know which one is my anode and which one is my cathode. Well, remember, in this case, we're actually really going to focus on which one is the positive electrode and which one is the negative electrode. Because if we remember that, if we look on the battery, we can help determine which one is the anode and which one is the cathode. Well, we know that the anode was negative in a voltaic cell. So that means an electrolytic cell, it has to be the opposite. So the anode is the positive. So my anode is going to be attached to my positive prong on the battery. So that means the silver is going to be my anode. And that means the spoon, which was positive in the voltaic cell, but is now negative in the electrolytic cell, is going to be my cathode. All right. So we labeled our anode, we label our cathode. Once you remember which one is your positive and your negative, just look at the battery to help you determine it. Then it says, with an arrow, show the direction of travel of electrons between the battery and the spoon. All right. Well, I know that based on the reading that the anode, the cathode draws in the electron while the anode sends it away. So that means from the anode is going to be sending the electrons to the cathode. So in that case, it's going to be going this way towards the cathode from the battery. I'm going to label this electron transfer. And that's basically it. You need to be able to identify which one is your anode, which one is your cathode, the direction in which the electrons flow, and obviously where each reaction is happening. So let's go ahead and let's differentiate the two. So we know that a voltaic cell, which is also known as the galvanic cell, is a spontaneous reaction. And we know that electrolytic is a non-spontaneous reaction. If you're confused on what a spontaneous and non-spontaneous reaction is, go ahead and look back at lesson 13's video to help you with that. Now, when it came to the electrode, the positive electrode was a cathode in voltaic, and now in the electrolytic, it is now the anode. And the negative electrode was in a voltaic was an anode. And the negative was a cathode. So you see how they're different, these three? Now over here, the rest of these three are not that different at all, because electrons still go from anode to cathode for both of them. Right? So A to C. I like to think of the alphabet. And over here, we still have red cat and an ox.